Okay, so welcome back. The plan for today is to finish chapters 8 and 9 on hypothesis testing and start correlation and regression. Um, I think probably what we're going to do today is talk about the cautions and pitfalls of hypothesis testing and probably leave chapter 9 to a supplement just depending on how much time we have. So I do have chapter 9 kind of written up here, but depending on where we are after this cautions and pitfalls discussion, I might point you to a YouTube video, say from a previous uh, class meeting or something, or might just make a new video on just chapter 9. Um, just recall that for these last couple of topics, so for instance, starting with chapter 9, testing for difference between two means, we're just intending to scratch the surface on these. So we're not going super deeply into the chapter 9 bit of hypothesis testing and testing for a difference between two means. We're not going super deeply into correlation regression, and we're not going super deeply into chi-squared or ANOVA tests. We're just kind of, throwing in just kind of surveying this material at the end of the course, just to show some jumping off points from this point forward. Okay. Um, So that's the plan for today. Wednesday coming up, we have finishing up correlation regression, starting chapter 11, chi-squared goodness of fit and independence. We might or might not get to that on Wednesday, just depending on how time progresses. But I did post the chi-squared recordings and ANOVA on the YouTube playlist. So if you want to, you can knock those out early. You can watch those lecture recordings from a previous semester. Those are already posted. Note that final exam week is essentially next week, but the final exam is open starting this Friday. So Friday the 6th, in a few days here, the final exam will be open so that if the weekend works better for you, generally speaking, you can feel free to take the exam over the weekend, or you can take it during the actual finals week. So whatever works best for you. Um, and a few details. Note that it's not comprehensive. It's only on chapters 7 through 12. It's the same setup as the midterm exam. It's taken on my stat lab using Examity. The sample final exam is available and has been available for a little while on my stat lab. So you can go on there, find the sample final exam. You can use it to help review the material for the exam. You can use formula sheets and distribution tables. I'll double check after class today, but I think those are available now on Blackboard, but if they're not, I'll make sure they're available by this afternoon. And as I've said a couple of times in the past about the midterm exam, don't wait until the last day or two to complete the final exam. Make sure that I would recommend planning to complete the final exam no later than Wednesday of finals week. So Wednesday the 11th, I guess. And that way, if anything goes wrong, you have a full business day or two to kind of get things worked out. Reach out to me, figure out a solution. You don't want to be taking your exam or planning to take it at Friday at 8 p.m. and something go wrong. And, obviously the final exam is worth a lot of your grades. So you definitely do not want to miss the final exam. Okay, so let me get my uh, screen's all set up here. I'm going to pop the PowerPoint presentation into chat. I think it also should be under the chapter 8 supplemental material folder on Blackboard, but this way you have it easily available for you. And give me 1 second to get my windows sorted out here and we'll get started. I don't know what my deal is today. I feel like it's been a week and I've forgotten all of my shortcut keys and everything. There we go. Okay, so the purpose of this discussion, this PowerPoint presentation, you can see there are 40 slides. I'm going to go quickly through some of the topics and spend a little more time on some other topics. But the purpose of this presentation is to hopefully for you to leave with an appreciation of how difficult it is to interpret hypothesis tests, interpret the result of hypothesis tests in a way that um, that is that is logically consistent with what the hypothesis test says. So where we're not making conclusions that aren't warranted by the logic of the hypothesis test setup, and also to convey those ideas, right? So if you imagine that, say, you're a researcher writing a paper, you have to understand it the correct way, and you also have to phrase things the correct way so that your reader uh, well, so that you're not saying things that are explicitly wrong, and also so that hopefully your reader will infer from what you're saying the correct thing. So it's quite challenging because of the complicated logical setup of hypothesis tests, right? The thing that we really want to say is something like, you know, I'm fairly certain that the alternative hypothesis H1 is true, but that's a Bayesian statement. We can't say that on the basis of hypothesis test. We can only say something like we've provided statistically significant evidence against the null and in favor of the alternative, or roughly speaking, that we've shown that that under the sample, or sorry, that under the null, the sample would be quite unlikely, and under the alternative, it's more likely. So it's kind of we're kind of saying the opposite of what we really, naturally want to say, and we have to be very careful how we phrase things so that we communicate that correctly, and it's quite difficult to do. So let's walk through just a couple of challenges with hypothesis testing and really the interpretation analysis of the results. The first is problems in a sense with alpha, with our significance level. Most journals accept alpha equals 5%. It's kind of a gold standard. In fact, there was a guy recently, somewhat recently, last maybe 5 or 10 years. He was some, fancy executive in a pharmaceutical company, and he tweeted, or whatever you call it now, he X'd or whatever, probably was still Twitter at the time. Um, Something about like, hey, we got significance in our clinical trial. Like, it's okay, no big deal, except that he was talking about significance at the 10% level instead of 5% level. And he got in a whole bunch of trouble for saying that because it's kind of like, okay, is that stock manipulation and all of that, right? So, um, so yeah, this alpha equals 5% is really kind of a gold standard. It's really almost a set in stone significance level uh, for a lot of fields. So for most journal articles that you read, the probability that the null was rejected, given that it's actually true, the probability that we're saying we found an effect, given that there's really no effect, is 5%, about 1 in 20. So this might lead us to the question, well, why 5%? Why this number? I mean, it doesn't seem like it's super mathematical. If it was some very mathematical approach, we would think that we'd get some strange number, right? Like 2% or pi squared over 4% or something. Why 5%? To the best of my abilities to research this, this basically came from Robert Fisher, a really great statistician, in some sense, the founder of frequentist statistics. And about 100 years ago, he made the following statement in his really important work, Statistical Methods for Research Workers, where he says a deviation exceeding the standard deviation occurs about once in 3 trials, twice the standard deviation about once in 22 trials. The value for which p equals 0.05 or 1 in 20 is 1.96 or nearly 2. It is convenient to take this point as a limit in judging whether a deviation is considered significant or not. So basically what he's saying is, okay, it's the 1920s. We can't, go to Excel and compute p-values or go to R or, right? I mean, computing a p-value in, 100 years ago would have required a lot of work. So what is he saying? He's saying, I'm writing this book. I've got to pick a cutoff for my book to say what's significant and what's not, and I'm going to choose two standard errors or p equals 0.05. So this is where a lot of people leave it. Fisher says 5%. But I think that there's a couple of points from Fisher that clue us into a little bit more, right? He says, using this criterion, we should be led to follow up a negative result only once in 22 trials, even if the statistics are the only guide available. Well, to follow up suggests that this is kind of an initial barrier to get over, not kind of like the end of the story, right? Also from Fisher, he talks about the salutary habit of repeating important experiments, of carrying out original observations and replicate, shows an appreciation for the fact that the object of the study is not the individual result, but the population of possibilities. We do our best to make our experiments representative. So um, I think it's clear to me that Fisher saw p less than 5%. Number one is maybe a little bit more like a convenient number to pick for the purpose of his book. You know, is it two standard errors away or not? Um, and maybe more generally saw it as a preliminary indicator to follow up research with more trials. In other words, almost like an exclusionary criterion. If you can't pass a hypothesis test at 5%, then just forget about this line of research. It's probably not going to yield good results in the future. Move on to something else. But it seems to me, at least the feeling that I get is if you get, you know, one journal article with statistical significance, people are like, oh, there's this new discovery, and, you know, that's that. And, you know, that's the end of the story. So we might want to be a little more cautious. As a side note, a medical literature kind of rule of thumb is that alpha equals 5% gives a beta of 20% or a power of about 80%. So a power of 80% means that 80% of the time the null is truly false, the test will correctly reject it. Now, of course, like when we're discussing power, that's also going to depend on things like effect size and things like sample size and so on. So, you know, there is a little bit of a positive feedback loop here that, you know, alpha equals 5%. We think that that means a beta of 20% or a power of 80%. So when we go to the statistician and say, how big do I need my trial to be? I'm going to say, how many, you know, folks do I need in my sample so that I get a power of 80%? So there's a little bit of kind of a self-fulfilling prophecy here. Everybody, you know, powers to 80%. So people tend to keep doing that. So there's a little bit of a feedback there. So let's take a look at an example. So suppose that a researcher tries 400 different drugs to see if a drug causes a patient to recover faster, and we'll assume these are just essentially randomly chosen. They want to test the mean time to recovery. The null is that the means are the same. The alternative is the mean time to recovery with the drug is less than the mean time to recovery without the drug. Our significance level will take to be 5%. And let's suppose that these drugs were kind of randomly chosen, so the null is true for all 400 drugs. None of these really help the patients. But a 5% significance level means there's a 5% false rejection rate. So out of 400 trials, we'd expect to get 20 false rejections. In other words, we think that we found 20, 20 drugs that work for this disease when really none of them do. Or what's the probability of getting at least one false rejection out of these 400? It's essentially a guarantee. We can recall some of our chapter 4 and chapter 5 probability work and remember how all of this works. Probability of at least one false rejection in 400 trials is 1 minus probability of no false rejections in 400 trials, and go from there. Okay, so what if we were to use a significance level of, say, 1 over 400 or 5% squared? This would be kind of like saying, okay, the drug has to pass a first hypothesis test. We have to reject the null in favor of the alternative. And then we publish that and we say, okay, this is a promising line of research. And then we let another research team take up the question using an orthogonal method, not using the same experiment that we used. And it has to pass their test as well at the 5% level. So it's like we have to overcome a 5% barrier and another 5% barrier. So that's like 5% squared. So as before, if the null is true for all 400 drugs, and alpha of 1 in 400 means there's a false rejection rate of 1 in 400, so out of these 400 trials, we'd expect to only get one false rejection, only one drug that, in a sense, makes it through both of these, makes it over both of these hurdles. Or what's the probability of getting at least one false rejection? It turns out to be around 2/3. Not great, but not a guarantee that we get at least one false rejection. So I think it's fair to say that alpha equals 5%. It makes a good screen. It makes a good indication that this is research we probably want to follow up on. But I don't think that it represents strong enough evidence by itself to be considered conclusive evidence. I think you probably want to wait until there's 2 or 3 more papers that come out and can replicate that and maybe verify it with orthogonal methods and so on with a different research team. Maybe then you feel pretty confident about it. So that's one thought about significance levels and p-values and so on. So moving on to the next topic, the idea of statistical significance versus practical relevance. So let's take a look at this example. Suppose for some hypothesis test, we have a null that the mean is 100 and an alternative, the mean is less than 100. Let's say, for instance, we're looking at a specific disease and we're asking, does it have an impact on cognition? Right? So maybe we're looking at IQ scores here. We know that the population mean IQ score is 100 for this IQ test. That's how it's set up. So if the disease doesn't negatively impact cognition, then our population of folks with the disease will have the same mean as the general population, mean IQ, say. But if it does negatively impact cognition, maybe our folks will have a lower mean IQ than general population. Let's suppose that the true mean for the folks in our sample is 99 point, or sorry, for the folks in our population with the disease is 99.9. And then we get the following sample, size 100,000, sample standard deviation of 15, X bar of 99.9. So X bar happened to be right on the mean here. The p-value under the null is 1.75%, highly significant. So we see statistically significant evidence that the true mean is less than 100. But the question here is, well, the true mean is actually only 0.1% less than the hypothesized mean. The difference is certainly statistically significant. We picked up the fact that it is true that mu is less than 100. It is true that the alternative is correct. But is it relevant? Does it have any practical relevance? Would we want to put in place any kind of intervention to stop this or research methods of keeping this, cognitive decline at bay in this population? Probably not. 1 part in 1,000 on an IQ test is not going to make any practical difference to patient outcomes or anything like that. I was listening to, I think it was the JAMA Statistical Evidence podcast. It was one of the JAMA podcasts, Journal of the American Medical Association. And I was listening to it, and what they do is they have the editor of this podcast in this journal series interview somebody. That's about once a month that they come out with it. They interview a clinician usually, or maybe a researcher, and they just talk a little bit about their research and statistical methods and so on. And there was a really interesting little sound bite. I should just, I should go and find a way to grab it and just record it and play it for you. But the setup is this. Basically, this person being interviewed is a clinician. They're an oncologist, so they see patients with cancer and they treat patients with cancer. So they're not just a researcher. They are actually, in the doctor's office treating patients on a day-to-day basis. And basically what the interviewer asked them is, okay, so there is so much information that comes out every week in the medical world. How do you decide which papers you're going to read and which ones you're not going to read, right? No person could keep up with all of the research 100%. How do you make that decision? And he said something really interesting. He said, well, I look at the sample size, and if the sample size is enormous, if it's like 1,000, 2,000, something like that, I pass over that paper. And it seems really strange, right? You'd say, wait, big sample size, isn't that really good? But this is what he's alluding to. Why is the p-value so low here? Well, because I have such a high sample size. My effect size is incredibly small. 100 to 99.9, that's a practically irrelevant effect size. That doesn't mean anything to a clinician or to a patient. Might be something of marginal interest to a researcher, but a patient doesn't care about this. They care about, you know, the really deleterious effects of the disease. If it dropped their IQ by 20 points, that would be huge. By 0.1 points, doesn't really matter. The clinician doesn't care about it. There's no reason to remediate this. They've got bigger fish to fry, so to speak. So there's this concept of a minimal clinically important difference. Is the difference that I expect to see from this intervention or from whatever it may be enough for a physician to change their clinical practice and to change the recommendations they make to their patients? And this guy's point was, if you went to your statistician, which all these folks do, they have these studies cost a lot of money. If you went to your statistician and said, I want to power this study at 80%, and your statistician came back and said, you need 2,000 people in the study to get that power, that means your effect size that you're expecting is incredibly small. You need a large N to tease out this effect. Well, if your effect size is incredibly small, the patients and clinicians don't really care about it. Maybe it's of a little bit of interest to a researcher, but that's not the symptom that the patient's going to say, I really want to avoid this symptom. There are going to be other symptoms of the disease that are more important. And that was basically his point, is if you go and power your study and your statistician tells you need thousands of people in your sample to get a power of 80%, say, the effect size, the practical relevance of that is likely to be extremely small. That means it's not worth his time reading that paper, because the effect size they're going to find is going to be so small that he might read it and say, oh, that's kind of interesting. But it has no positive effect on his practice or his ability to treat patients or his patients' outcomes or happiness. He wants to focus on the inputs, on the information that's going to change his practice and better his patients' outcomes. Okay, so one thing that I think can be taken from this is be a little bit cautious about big data. Especially these days, it's really easy to, you'll see papers with sample sizes of 30,000, 50,000, 100,000, because they just wrote a program that scraped the electronic medical record for some big hospital system, right? And it just went through and said, does the person have this disease or not have it, and what do their outcomes look like? And you can get enormous sample sizes just from scraping a whole electronic medical record, particularly for a disease that's not a rare disease. If you're looking for heart disease or, something like that, or diabetes, or, you're going to get lots and lots. You're going to get tens of thousands of patients in a big hospital system that have that disease. So you might get a p-value that's extraordinarily small, highly significant, 1%, or even p-values look like this, like 10 to the minus 11, extremely significant. But the question is, when you have that big of a sample that you're working with, being extremely significant does not mean that it's extremely relevant. It could just be that in some rough sense, we're extremely certain, that's a Bayesian statement, but let's just let it slide this time. In some sense, we're extremely certain that the mean is less than 100, but because the sample size is so big, the mean may well be only a teeny tiny bit less than 100, not enough for us to care about practically. So beware of big data. It's much more meaningful or something like that at first glance if you see a sample size of 50 and a p-value of 3% or 1%, than if you see a sample size of 1,000,000 and a p-value of 10 to the minus 5. And as a side note, to be fair, from the results of hypothesis tests, no real information or estimate is translated transmitted about the size of the true mean. But to be fair, most journals will report the result of the hypothesis test, the p-value, as well as a confidence interval for the mean. So that does give you an idea of what they expect the mean is. Does the confidence interval look like 99.9 plus or minus 0.0001? Or does it look like 95 plus or minus 3, right? Those are very different results. This is kind of a side note. We'll kind of gloss over this one, but we know that there's a trade-off between alpha and beta. If I push the type 1 error down and all else is equal, if I don't increase my sample size, type 2 error goes up, and vice versa. Kind of like with a jury trial. If I require a higher bar to be passed in order to declare the person guilty, well, fewer innocent people are declared guilty, but also more guilty people go free. And vice versa. If I have a lower bar to declare guilt, there's going to be more innocent people declared guilty, but there are going to be fewer guilty people go free. So there's a trade-off between those two errors. So how should we treat this? Should we minimize something like total error, alpha plus beta? Should we minimize some cost function of the errors, like the cost of alpha, the cost of type 1 error times type 1 error rate, plus cost of type 2 error times type 2 error rate? Maybe that makes more sense. In areas where a type 1 error rate is extremely costly, maybe we really want to minimize alpha and we'll let beta get pretty big if it's relatively much less costly. In other areas, it might be just the opposite. Maybe a type 2 error is very costly. We'll minimize beta at the expense of a higher alpha. And this is just an example showing that if you want to minimize the total error, roughly speaking, you choose the intersection of the two PDFs as your kind of cutoff point. And there are a couple of examples here where, say in a jury trial, at least in our culture, we think of the cost of a type 1 error, the cost of putting an innocent person in jail as being much higher than the cost of letting a guilty person go free. For something like a TSA screening, the cost of a type 1 error, the cost of saying, hey, something looked a little wonky on your scan, can you come over here for like a pat down, right? That's relatively speaking a lower cost than, say, the cost of a type 2 error, letting somebody with a bomb or with a gun or something get through security and get on a plane with that. Medical tests is kind of hard to tell, right? You imagine, say, like a screen uh, for say cancer. Well, on one hand, we don't want to miss cancer, so we maybe are very sensitive in that regard. Maybe we're willing to tolerate a high false positive rate. But also, if I'm telling everybody that they have cancer, number one, they might not, they might say, okay, well, I've heard that, most of the time that this test comes back positive, it's not cancer, so they might not even go to their follow-up. Or, even if they do go to their follow-up, maybe they get an appointment in a month and they're super stressed out, have trouble sleeping, have trouble with all kinds of stuff for that next month. And maybe it's very costly for them to go to that follow-up, financially. So there are costs on both sides of things. And, I don't think that's an easy answer for a lot of medical tests. Uh, yeah. So again, I mean, I think that a sensible thing is to, change your alpha and beta based on the costs of type 1 and type 2 errors. But that's usually not done, right? Usually we kind of peg alpha at 5% and that's that. The downside of this is that somebody being malevolent could say, well, I want my alpha to be high, so I'll just say the type 1 errors are really costly and therefore I increase alpha and it makes it easier for me to get statistical significance. So that's the downside of it. Somebody could game the system. Any questions so far? I think one of the biggest challenges with hypothesis tests is misinterpretation of p-values. And the reason is that we kind of want to say because the p-value is small, then it's unlikely that H naught is true. Or in other words, because the probability of seeing this evidence, if the null was true, is low, then the probability that the null is true, given that I've seen this evidence, is also low. But if we look at these probability statements, we realize we can't say this. I flipped my conditions around. This is really a Bayesian claim. I need to apply Bayes' theorem. To put it in the jury trial analogy, this is sometimes called the prosecutor's fallacy for this reason. For example, it's not correct to make the following claim, since it's very unlikely for all the circumstantial evidence to exist if the person were truly innocent, then it's unlikely the person is truly innocent. That seems like a very reasonable and logical statement, but it's completely false. It's a fallacy. It doesn't hold true in all instances. Oh, jumping ahead. So let's look at an example here. Suppose there are two competing hypotheses. The null is the person is innocent of bank robbery. The alternative is the person is guilty of bank robbery. Let's suppose there's a plethora of circumstantial evidence, and it's estimated that the probability of seeing this evidence, given the person is innocent, is 0.5%. So maybe somebody saw the bank robber leaving the bank and they said they're about this height with this hair color. They got in this color car, and this person is that height, has that hair color, got in the same or owns the same color car. And we estimate that all of that would line up against a random person from the population only at a rate of 0.5% or 1 in 200. As frequentists, we would say this is highly significant. We reject H0 even at the very high bar of a 1% level of significance. But again, really, this is a Bayesian statement. Let's take a look at this from the Bayesian perspective. We want to prove guilt beyond a reasonable doubt. So we want to prove that it's very unlikely the person is innocent. In other words, something like probability of innocent given evidence less than some small number. Or in other words, probability of guilt given evidence bigger than 1 minus some small number. Let's suppose that we interpret beyond a reasonable doubt as more than 99% likely. Again, this is a Bayesian statement. This is saying the likelihood the person is innocent, or yeah, the likelihood the person is guilty, let's say, given the evidence, is more than 99%. This is not the same as rejecting with a p-value less than 1%. This is not the same as saying the probability of seeing this evidence for an innocent person is less than 1%. One of the problems here is that most people don't rob banks. So if we had no other evidence, we consider it pretty unlikely the guy's a bank robber. So I pulled the FBI, bank robbery data, and it turns out that not very many people are bank robbers. Less than 1 in 10,000 people are bank robbers. So let's just set probability of guilty at 0.01% and probability of innocent at 99.99% as our priors. And let's look at the probability of guilt given evidence now. Now you might look at this and you might say, wait, well, hold on a minute. We have to choose priors. That's one of the difficulties of the Bayesian approach, is what prior should I choose? It seems a bit silly to choose priors like this when the person's on trial for bank robbery, right? Are they really just a random member of the population if they've been suspected of bank robbery, arrested by the police, investigated, charged by the DA, the judge saw the evidence and allowed the trial to proceed? That's a lot of hurdles to get through, just to get to this trial. This person on trial, they're not just a random member of the population, are they? Well, I would argue that this is the proper prior distribution, and there is an argument to be, there are different arguments to be made here. But I would argue this is the proper prior distribution to use, that at the beginning of a trial, at the outset, before anything else is known, we should just presume that this person on trial is a random person chosen from the population. And this is why the purpose of the trial is to present evidence against the defendant, right? Well, I mean, the police had some evidence that led them to suspect this person and arrest them. Presumably, that evidence is going to be presented at trial. The DA had some evidence that they used to charge the person. probably some of that evidence is the same evidence the police officer used to arrest them. And they probably got some more evidence out of the investigation, and that was their argument to charge the person. The judge saw some evidence, probably what the DA had and the cop had, and probably even more. And the judge said, I'll let the trial move forward based on all of that evidence. And then the trial is going to present all that same evidence again, presumably. That's the prosecutor's job, is to present that evidence. So if I say something like, well, at the outset of the trial, they've already been looked at by the cop and the DA and the judge, so I can't treat them as a random member of the population. How many times have I counted the evidence already that the cop saw that probably was part of the DA's analysis, and that was probably part of the judge's analysis, and then it's going to be presented again at trial? How many times am I going to recount the same evidence if I treat this person on trial at the beginning of the trial before any evidence is presented at the trial as already suspect, right? I would argue at the beginning of the trial, we should treat them as though they are just a general member of the population and adjust probabilities from there on the basis of what the prosecutor presents. We shouldn't look at the person and say, oh, they're probably guilty because they're up there. And then, in addition, allow all of the piece of evidence presented at trial to further influence that, because that evidence has already largely or partly been used to put that person on trial. So this is my argument in favor of that. Again, maybe some others would have a different argument against it, but going off of this basis, what's the probability the person is innocent given the evidence? We can do a Bayes calculation. You can look through the details here. Work through the details on your own. It's good practice. But it turns out that the probability the person is innocent given this evidence, this p-value of 5%, is 98.03%. The chance that they're innocent. So the probability they're guilty in light of this evidence, in light of a p-value of 5%, or sorry, of 0.5%, is the probability they're guilty under the Bayesian perspective is only 2%. This is the number we were looking at, needing to be over 99% for the Bayesian to declare guilt. The frequentist rejected all in favor of the alternative, but the Bayesian is nowhere even close. There's only a 2% chance the person is guilty in light of this circumstantial evidence. Nowhere close to that, say, 99% cutoff. What's the difference here? The Bayesian is looking at this prior probability distribution that most people don't commit bank robbery. The frequentist does not look at that information at all, right? The frequentist would say probability of evidence given innocent of 0.5% is the same result whether we're accusing the person of bank robbery or speeding 3 miles an hour over the speed limit. But we kind of understand that far fewer people commit bank robberies than go 3 over the speed limit, right? I mean, if this was going 3 over the speed limit, like, probability of guilty is probably 99% and probability of innocent is like 1%. You could almost just pick a random person, put them on trial and say they went 3 over the speed limit, and you'd probably say, yeah, probably at some point in the last week they did, to be fair. That's not how our legal system works, but I mean, probabilistically, you could basically pick any random person from the population who drives, and they've probably gone 3 over the speed limit at some point in the last week. Okay, so we might ask the question that, okay, well, so certainly with more circumstantial evidence, certainly with a lower p-value, the Bayesian will also be more convinced that the person is guilty. How unlikely does the circumstantial evidence have to be? In other words, how small must the p-value be to convince the Bayesian that the probability the person's innocent is less than 1% or the probability they're guilty is more than 99%? And this is the calculation that we want to do. We want to solve this, set this equal to 1% and solve it for x. And we get approximately 1 in a million. So in like a reasonable sized city like Pittsburgh, basically your circumstantial evidence has to be strong enough that they're the only person in the city that fits all of that circumstantial evidence. As a side note, we're also assuming that the circumstantial evidence is all correct. And we also know that witness testimony isn't the best, right? They might say the person had red hair and they actually have blonde hair, or they might say they drove away in a red Toyota and it might have been, an orange Ford. So we're we're not really taking that into account either. The fact that some of these pieces of evidence might just simply be incorrect. Right. So essentially our circumstantial evidence would have to be so strong that in a moderate sized city, they're the only person in the city essentially that would match all of that circumstantial evidence. So the Bayesian would require essentially a p-value of 1 in a million, where the frequentist would require a p-value of, say, less than 1%. And here's a little XKCD joke. The XKCD is, they publish kind of nerdy comics. So if you want to look up, xkcd.com and see some of their comics, they're usually pretty funny. But did the sun just explode is the name of this comic. It's night, so we're not sure. So the first guy says, this neutrino detector measures whether the sun has gone nova, and then it rolls 2 dice. If they both come up 6, it lies to us, otherwise it tells us the truth. Let's try. Detector, has the sun gone nova? They push the button. It rolls the dice, it says yes. The frequency statistician on the left says the probability of this result happening by chance, a false positive, is 1 in 36, right? Chance of rolling 2 6s is 1 in 36. 0.027, since p is less than 0.05, I conclude the sun has exploded. And the Bayesian statistician on the right says, I bet you $50 it hasn't, right? As an aside, it's always a good bet to bet that the sun has not exploded, because if it has exploded, you're going to be like vaporized or whatever in 8 minutes or so. So you might as well always take that bet that it hasn't exploded. But this makes the point, right? That the chance of the sun exploding in the next couple minutes is probably extraordinarily small. But the frequentist statistician doesn't look at that at all. We just know that the sun's not going to explode in the next couple minutes. Like it's almost a certainty. But the frequentist doesn't care whether that's what we're evaluating or whether we push the button on the machine, and whether we're asking it, again, something like, did Bill over there, who drives, an hour to work each day, go 3 miles an hour over the speed limit at any time in the past week, right? It's the frequentist statistician doesn't look at any of that. The Bayesian statistician does. Another example that I've heard in the past that it's a silly example, but it's like, it illustrates the point, is if somebody comes up to you and says, I'll bet you $1, I can flip a coin and get 10 heads in a row, and you say, sure, and they do flip the coin and get 10 heads in a row and win your dollar, what's the chance that that coin is imbalanced, right? It's going to be a very different suspicion whether it's like the slimy guy at the bar or whether it's like your 2-year-old niece, right? I mean, like, is your 2-year-old niece really going to have the means and the thought to go and, get an imbalanced coin and try to scam you out of $1? I don't think 2-year-olds are quite that smart or malevolent yet. Um, but if it's the slimy guy at the bar, it's like my suspicion is going to be much higher. My prior probability of them having an unfair coin is going to be much higher than, if my niece comes up and does it, she probably just got really, really lucky and flipped the coin, flipped 10 heads in a row or something. Okay, so I think that was the last really big point. Couple more points. One on publication bias. So let's look at an example here. Suppose I told you I ran a study. I gave my medication to test subjects who were very ill. 50 of them recovered within 24 hours. The typical recovery time for this type of illness is 1 week. Does this represent strong evidence for the efficacy of my drug? And I think most of us would look at this and see the problem with this statement. Well, I've reported to you the positives. I've reported to you the number of people who it seems like my drug worked really well for. But is that 50 out of 50 that are in my trial, or is that 50 out of 10,000? That puts a very different spin on it, right? The negatives are at least as important as the positives. The folks that my drug didn't work for and that took them a whole week to recover are at least as important as the folks that my drug did work for. again, if the trial consisted only of 50 people and they all got better at 24 hours under my drug and the typical time to recovery is a week, then yeah, like I mean, it passes the interocular test uh, as one of my professors would say. It just the numbers jump out, hit you between the eyes. You don't need to run a hypothesis test and run the numbers to tell, yeah, this is significant. If every single person got better in one day instead of 1 week, yeah, your drug works. On the other hand, if there were 1,000 participants and 50 got better within 24 hours, I don't know. Like that may have been just a chance event. Maybe the drug does nothing, and some of the people just bounce back a little quicker. So the number of positive results only tells half the story. As kind of a side note, back in COVID days when the tests were pretty scarce, the tests for whether you currently had COVID, actually one of my friends who's an actuary, so he deals with statistics and numbers and all of this stuff all the time. He made a couple posts on Facebook that basically said, oh, look at all these positive test results and the positive test result proportion and all of that. And basically I had to point this out to him, like, dude, I get what you're saying. I don't disagree with you morally, but you're sharing bad stats here. You got to do better science than this if you want people to listen to you. You're only looking at the positives, and you're looking at the positives, not the negatives, and you're looking at a non-representative sample, because when the tests are scarce, they're only giving the tests to people that they're already highly suspicious have the disease. So the number of negatives is really important, and it's very easy to fall into a trap like this in real world situations. I mean, he's a bright guy. He's, works with numbers and stats all the time, but he didn't, see that going into it. And I'm sure there are things that I've posted or said where I've, made the same slip up. So where does this come in? I mean, we say, okay, well, this is kind of silly. Like most people would kind of see that flaw right away. But what if we zoom out a level and instead of saying in one study, we're looking at 1,000 participants or 50 participants, and we just see the 50 positive results. If we zoom out a level and we say among all studies that I see, I go to PubMed and I search for whatever disease process I'm interested in or treatment I'm interested in, and I come up with 5 positive studies, 5 studies that said, hey, we investigated whether this treatment works and it does work. Isn't that awesome? Is that 5 positive study results out of 5 researchers who ran a study? Or is that 5 positive study results out of 100 researchers who ran a study? Right? Researchers who run an experiment and don't get a result quite often don't publish their results, or at the very least, they're not going to be published on the cover of Nature or JAMA or NEJM. They're going to be published in some, goofy little journal somewhere that, nobody knows about. It's the big, new discoveries that get the front page. It's not the repetitions of experiments, and it's not the failed results. So are those 5 positive results, those 5 positive studies that found an effect, is it 5 out of 5? Is it 5 out of 7? Is it 5 out of 100? If it's 5 out of 100, that's just chance, right? That's our alpha of 5%. That's essentially meaningless. If it's 5 out of 5 or even 5 out of 7, that's quite meaningful. How do I know what those negatives look like? I really don't. There's a publication bias. The positives tend to get published and get a lot more fanfare than the negatives. In recent years, a few journals, but not many and not really the big ones, have basically said, okay, if you want to publish your result in our journal, when it's done, when your experiment is done, you have to register your experiment with us before. So you have to tell us you're doing the experiment before, and then when you complete the experiment, if you get a really cool result, we'll publish it. But if you get a really cool result and you didn't register with us at first, then we're not going to publish it no matter how cool your result is. So it's an attempt to get an idea of the negative results, right? If you have 1,000 studies in this area registered and 50 of them got a positive result, well, that's just chance. If you have 1,000, studies in this area registered and, 350 of them got a positive result, maybe that's indicative of something, right? So yeah, so an important problem, but um, still not a really great, still not a really great answer to it. And just kind of as a side note, in some sense, what at least one facet of what defines science is if you believe something, you try really, really hard to prove your belief false, right? I'd say, if I had to say what characterizes science in one sentence versus say other means of supporting belief, I think that's probably it. I believe something and I try really, really hard to prove myself wrong, to prove my belief wrong. Well, when we go to PubMed or something like that, if we're just looking for, treatments for this disease or whatever it may be, um, in some sense, we're almost like trying to prove ourselves right. It's kind of the opposite of science. So we have to be just really, I'm not saying that we shouldn't do that. I'm saying you have to be a little careful, a little cognizant of that there might be a lot of unpublished material, negative results floating around out there. So don't, latch onto one or two studies too strongly. And then last but not least is just the awkward logic hypothesis test makes them pretty hard to understand and interpret. The math isn't that bad. As we saw, it's essentially the same math as say confidence intervals or a normal distribution calculation, but it's really the interpretation and analysis that's the difficult part. So roughly speaking, what we do is we assume the opposite of what we want to show is true. Usually we're looking to show evidence in favor of the alternative, and we assume the null is true. We gather data, we analyze how strange it would be to obtain this sample if the null was true, and it would be very unlikely under the null and more likely under the alternative, then we reject the null in favor of the alternative. It's a very backdoor approach. It's an argument by contradiction. So why are they used? Well, despite all these problems, or maybe we just say challenges, there aren't a whole lot of options available. Bayesian analysis is often seen as subjective because we have to pick a prior. In the same way that somebody could say game a hypothesis test by choosing alpha however they want, but we can peg alpha to 5% and say everybody use this one. That's the bar. It's much harder to say, well, what prior should we use for this or that scenario? So it's dependent on priors, and the researcher gets to choose the prior. And who's to say that they choose a prior that they really think is true versus one that's going to make them look better, make their result look better? Um, or who's to say that even if they approach it in good faith and say, I choose this prior to work with, somebody else could very well approach it in good faith and choose a different prior. They might have a different set of life experiences or set of research experiences that lead them to different assumptions of what the prior is. There's an area choosing robust priors, so trying to choose priors in such a way that, in essence, when you get evidence, the prior fades most quickly into the background and the evidence most quickly takes kind of the front seat, so to speak. But that's not easy to do. Uh, Also, the status quo is frequentist analysis. If we just start running Bayesian analysis for everything, how do we compare our results today to results 5 or 10 or 20 years ago? It's more difficult if we just kind of make a paradigm shift like that. Historically speaking, frequentism was chosen over Bayesianism because Bayesianism, not really the level of Bayesian analysis that we did, but a lot of the Bayesian techniques require a lot of computer power. These days, that's not a problem. You just have a laptop sitting on your desk, you type in some code, you hit enter, you go to sleep, you wake up in the morning, it's done. But in 1970, that was a much bigger deal, right? You might need time on a supercomputer. You might need to put in a request for time at your research facility and write up a whole bunch of punch cards and all of that, right? Like you run all of your punch cards and you get the result at the end and say, oh, I had one punch wrong on one card, so now the whole thing is wasted. I have to do it again. Or in 1930, like, well, Bayesian methods probably weren't really around then, but it didn't really have that ability really at all to do, say, that far back. On the flip side, so I've kind of, denigrated hypothesis tests for the better part of an hour now. To be fair, to give them their due, well performed and well analyzed and well interpreted and well communicated, all of that, hypothesis tests generate solid results. I mean, this has been the standard for 100 years, and I think most people would agree that, say, in medical science, for instance, like we know how to do a bunch more things today than we have in the past. Like we're much more successful at curing a lot more diseases than say 20 or 50 or 100 years ago. I think most people would agree with that statement. So it seems like, we're moving forward. And alpha of 5%, why do we choose that? Well, that gives us a power of 80%. That seems like a pretty nice balance. Being 80%, finding 4 out of 5 of truly false nulls. That seems like a pretty good outcome. And we're not sacrificing too much in terms of alpha. Maybe we would love to drive alpha to 1%, only get one false positive out of 100, but what's the power going to be then? How much is the power going to suffer? Or on the flip side, how much more money and effort and time, and frankly, patient risk am I going to have to put into that study? The larger my study is, I mean, every study where I'm performing an intervention on a patient puts that patient at some level of risk. I have to risk more patient harm to get, say, the same power for a smaller alpha. So there are a lot of trade-offs in play here. Okay, so let's look at an example here. Suppose that the prior probability that the null is true is pi. So it's not pi at 3.14, it's pi just the letter p basically. But since we have p being used for p-value and for all kinds of things, the prior probability is typically the letter pi, which ironically in Greek is really pronounced p anyway. So, but if I start calling it p, then it's going to get confused with our p. So probability H not true is this variable, just this letter pi. The probability that H naught is rejected, or sorry, the H naught is false, given that it's rejected. So if the frequentist rejects the null, what's the Bayesian's interpretation of the probability the null is false based on that? It's kind of like the circumstantial evidence. If the circumstantial evidence, the p-value is 0.5%, the Bayesian said that for the bank robber, the chance of them being guilty was like 2%. That's what we're doing here. So for a given prior probability that the null is true, if the frequentist rejects the null, what does the Bayesian say is the probability that the null is false? So if the Bayesian would say the null is false when the frequentist rejects it, if that probability is high, then essentially the Bayesians and frequentists kind of agree, morally speaking. They might come up with different numbers or something, but morally speaking, they both agree the null should be overturned in favor of the alternative. And this is what that turns out to be, 80 minus 80 pi over 80 minus 75 pi, under the assumptions of alpha 5% and beta of 20%. So again, if this number is high, if it's up here close to 1, that's when the Bayesians and frequentists essentially agree and say, yeah, we're in agreement on the result of going with the alternative instead of the null. Again, they might have different numbers and different calculations to get there, but they agree morally speaking. We see agreement. I mean, maybe you say up here at 90% level, 90% agreement at maybe a pi of 0.3 or so. And at a pi of 0.5, a 50-50 shot, we're probably up around 95%, right? For pi of 0.5, for a prior probability that says we're 50-50 on whether the null is true or the alternative is true, if that's how the Bayesian viewed it, null and alternative are equally likely. So anywhere from that point up to the Bayesian saying that it's very unlikely the null is true. So that's the right-hand side over here, null being 50-50, all the way over to being extremely unlikely the null is true. Well, then they're in agreement at about the 95% level. Like the Bayesian is going to say, I'm 95% confident or more that the alternative is true. And the frequentist would reject the null in favor of the alternative. They would agree quite well from basically a coin flip or more extreme against the null. They'd agree decently well at about maybe a 30% chance that that the null is false. It's really way over here on the left where we see these probabilities get very low, where the frequentist would reject, but the Bayesian would say, no, that I'm sticking with the null, and the frequentist would say, no, I'm going with the alternative. It's over here on the left where X is very small, where the probability H naught being false, the prior probability H naught being false from the Bayesian perspective is very small, or where the prior probability of H naught being true is very large from the Bayesian perspective. Just like in the bank robber example, where the probability of the person being innocent of bank robbery is very large, probability of them being guilty of bank robbery, probability of them of the null being false is very small. That's where the Bayesian says, even with your circumstantial evidence, I'm still not convinced, but the frequentist would be convinced, right? Over here on the left, say under 20 or 10% is where we see the disagreement between the Bayesians and frequentists. When the null is, say, 80 or 90% likely or more from the Bayesian perspective, from the prior probability, that's where you're probably going to get disagreement between the Bayesians and the frequentists, because the frequentist will overturn the null that the Bayesian gives a 90% probability to, or a 10% probability to. The frequentist will overturn that null for the same p-value. They don't look at any of those prior probabilities. But again, like for reasonable nulls or for reasonable hypotheses that are set up where the null is not overwhelmingly likely to be true based on our previous experience, the Bayesians and frequentists honestly kind of morally agree a lot of the time. They're going to reach the same results. Okay, any questions or thoughts on hypothesis tests? All right, let me switch my screens around here a little bit. We're jumping into correlation and regression. Let me also grab a couple, I need to open up chat again. Let me grab a couple Excel files and post them in the chat. I don't know if we'll get to these today or we might get to them next time, but if we do get to them today, they will be in the chat already this way, so you can download them and then just hang on to them for next time if you if we don't get to them today. Okay, so there's one that I posted already and two more that are in there now. Okay, got lots of screens to manage today, so thank you for your patience while I get all of this combobulated. I also need to do everything in the right order because if I have the file open before I post it in chat, Zoom doesn't let me post it if it's open, so which I quite often forget about. Okay, so we're moving on to, if there aren't any questions on hypothesis testing, which it doesn't look like there are, we're moving on to chapter 10, correlation regression. As I kind of mentioned before, like most of these little topics at the end, this is a really big topic. I mean, you could do, a couple semesters of graduate work, graduate school level work in correlation regression. You honestly could probably do a master's or a doctoral degree in things related to correlation regression and linear modeling and things like this, things kind of related to this. So this is really a huge field, and we are just scratching the surface. We just want to understand what is the goal of these models, of these numbers and models? What do they attempt to do? And maybe what are some cautions? How do I tell if a given model is a garbage model or a good model or something in between? Okay, so correlation regression, what is the overall goal? Our overall goal is to study the relationship between two variables, X and Y. And in particular, and importantly, to study the linear relationship between those two variables. So this is actually a quite important bit here, studying the linear relationship between the variables. So what are our inputs? Our inputs are data consisting of ordered pairs. And we know that the, cannot draw today. Have my trackpad at a funny angle. There, it's a little better. Okay, So inputs are data consisting of ordered pairs, and we can graph those on a scatter plot. So we would have data points x, y, and we would have like, you know, say point number 1, point number 2, point number 3, down to point number n. And maybe this is say like height and weight. That's the classic example. So I take person number 1, I measure their height, I measure their weight, I write those down, and those both are characteristics of person 1, so they're inherently tied together. It's not like I take 100 people measure their heights and then 100 different people measure their weights and then just like stick the two data sets next to one another. It's like there's an inherent tie between this. It's person number 1 has a height and a weight, and maybe it ends up here. And person number 2 has a height and a weight. Maybe that's there. And we expect, most of the time that taller people weigh more and heavier people tend to be taller. So maybe we see a scatter plot like this. And my question is, what does the linear relationship between these two variables look like? What's the nature of the relationship? Okay, so the first thing that I'm going to look at to describe this relationship is called the correlation coefficient. So the population correlation coefficient gets the name rho. It's the Greek letter R. It looks a little bit like a P with kind of a curly tail. So the Greek lowercase r, rho, that's for population. And the, I don't know, Latin alphabet, whatever you want to call our alphabet, R is the sample. So our R, little r, is the sample correlation coefficient. For the purposes of this lecture, I'm not going to really point out or be careful to use rho versus r in a careful way. Again, we're just scratching the surface here. It's important that by the mathematical definition of these things, they are always between -1 and 1 inclusive. Kind of similar to how by the definition of probability, it's always between 0 and 1 inclusive, or by the definition of standard deviation, it's always bigger than 0, greater than or equal to 0, I suppose. Similar idea here. These are always between -1 and 1 inclusive. And it has this goal to describe the degree and the nature of the linear relationship between the variables. So is there a linear relationship between the variables? If no, then there's a low degree of relationship. And if yes, there's a high degree of linear relationship. And if there is a linear relationship, particularly if there's a high degree of linear relationship, what is the nature of that relationship? So we have two characteristics: magnitude between 0 and 1, describing the degree of the relationship. In other words, if I take a number between -1 and 1, and I take its absolute value, its magnitude, its size, just basically chop off the negative or whatever sign in front of it, I get a number between 0 and 1. That's the magnitude. So 1 is a high magnitude of linear relationship between the variables, 0, very low magnitude. And sign, positive or negative, tells me the nature, tells me how the two variables are related. Right. Magnitude near 1, in other words, rho near -1 or rho near +1. In both directions, I would have a magnitude that's near +1. So when my magnitude is near 1, that's a high degree of linear relationship. Or when the magnitude is near 0, that also essentially means that rho is near 0, either a little bit positive or a little bit negative, but in both cases, we'd say near 0. There's a low degree of linear relationship. So near one, there's a high degree of linear relationship. Near zero, there's essentially no linear relationship. And we might say then if the magnitude is near one, if it's high enough, maybe 0.7 or 0.8 is our cutoff, maybe 0.5 is our cutoff for being near one. I don't know. That might be situation dependent, but if our magnitude is near one or near enough to one, then there is a linear relationship and we can describe it. We can talk about its nature. If it's near zero, there's no real relationship, so we don't really talk about the nature of the relationship if it's non-existent. But if the magnitude is near one, we can describe its nature. If rho is near plus one, the nature is positive. And if rho is near negative one, the nature is negative. And I'll give a little more sense of what I mean here, because all that I've kind of done is said the same thing twice. So just let me give myself a little more room here. So of course, if rho is near positive one, the nature is positive. If it's near negative one, the nature is negative. That doesn't really tell me much. Here's what I mean when I say a positive relationship. I mean, larger values of x tend to be associated with, I'm being careful how I say this, larger values of y, and vice versa. Is it VI? I think is it VICE versa or VISC? I don't know. We'll write it that way. That might be the wrong way to say it. So larger values of x tend to be associated with larger values of y, and smaller values of x tend to be associated with smaller values of y. It's positive in the sense that the relationship is the same way, right? So this would be like a positive relationship, height and weight, because people who tend to weigh more tend to be taller, and people who tend to be taller tend to weigh more. A negative relationship is the opposite. Larger values of x tend to be associated with smaller values of y. And vice versa. Just write VV since I forgot how to spell vice, which way it's spelled. So a rho near negative one is where there's like a trade-off, where having more of one thing is typically associated with having less of the other thing. I've been kind of careful here to say this in a particular way. It's maybe a bit of a pet peeve of mine, but I think it's an important note. A lot of people say something like a positive relationship is where as x increases, y increases. That's a very misleading way to say it, I think. At best, it's misleading, and at worst, it's simply wrong. Because we're saying something increases, that brings in a temporal element. It's almost like we're watching, like if we're watching, one person over time. I mean, I guess if you're a kid, you over time tend to like increase in height and increase in weight. But like but that's not the sense that we're getting at here. We will be saying if I have 100 kids, kids who tend to be taller tend to be heavier. There's not really an increase in height or weight. It's not like, right, I'm looking at discrete data points. It's not like if I move a slider, either forward in time or forward in height or something, um, that's not really what my data is saying. So I don't like to say it that way because, neither X nor Y are increasing or decreasing. They just are what they are. But what we're measuring here is the association between these variables. And in a positive relationship, larger values of x tend to be associated with larger values of y and smaller with smaller. Where in a negative relationship, larger values of X tend to be associated with smaller values of Y and smaller with larger. Right. Okay, so let's take a minute here. Let me switch screens yet again. I have a lot of screen switches today, so sorry about that. This tends to happen when I am using Excel. And let's bring up the correlation demo that I posted in chat. All right, so let me share this. I think I'm just going to share my whole screen now. I think I can do this, and it's fine. So this is some old data. You can see this is from 2013. And this is stock market data. So here is, for instance, Google versus gold. Gold, by the way, GLD, gold is Spider Gold shares. So it's kind of like roughly speaking, a stock that you can buy where the company just like buys physical gold and stores it in a vault. So you're kind of buying gold, but you're buying like, a stock that represents a share of a certain gold holding. So this company Spider, they have this ETF, this exchange traded fund, GLD gold. So these are Spider Gold shares, their value. And we see that if we look at their scatter plot, Google versus gold, it seems like just kind of a big blob. And if we calculate the correlation, it's negative 0.01. So that correlation, negative 0.01, that has a magnitude near zero. Not really sensible to describe the nature of the relationship because I don't think there really is a linear relationship here. How did I calculate this correlation? We're not going to go into even the formula for calculating it by hand. There is a formula, it's probably in your book, but it's long and cumbersome. We're going to use the Excel correl function, CORRAL, for correlation between this data set, this list of gold share values, and this list of Google share values. So I ask for the correlation between that, CORRAL of B2 to B54 and C2 to C54. And that gives us this negative 0.01. That's quite close to zero on a scale from 0 to 1, right? That's like 1.5 percentage points. That's very close to zero. Not a very good linear relationship here. Gold versus Microsoft, negative 0.08, still pretty close to zero. And our scatter plot, we look at it and we say, yeah, it still doesn't look like things are really, it doesn't look like there's much of a linear relationship here. Microsoft versus Google, negative 0.32, the magnitude is about 0.3 on a scale from 0 to 1, getting a little closer to 1 in magnitude, but still pretty low. Google versus Yahoo back in 2013 when Yahoo was still a little bit relevant. And we're starting to actually see a bit of a linear relationship here. Like I can imagine, if I ignore some of these dots on the top left here, this looks pretty much like a line. The correlation is about 0.8. Say PIMCO versus Microsoft. This is PIMCO's high yield bond fund. So PIMCO is a company that sells mutual funds that hold bonds, they sell bond funds. And this is a high yield bond fund. And we see the correlation of PIMCO with Microsoft. It looks a little messier. It doesn't look like as nice and tight of a line as this one here. We see the correlation of about 0.7, right? Both Google and Yahoo and PIMCO versus Microsoft, it seems like they both have a correlation coefficient that is somewhat close to 1 in magnitude, 0.6, 0.7, 0.8, something like that. That's getting up close to 1. So it does seem like there is some linear nature to their relationship. And we see in both cases, since there is a linear relationship and makes sense to describe it, in both cases it's positive. When one share price tends to be high, the other tends to also be high, and vice versa. When one is low, the other tends to be low for both of these cases. You can also pull up the, let me switch my share for just 1 second here. Sorry for all the switches, but I have a bunch of different Excel files today. You can also pull up the one that's titled Regression Demo that I posted. Oh, it comes up kind of funny, but if we pull this one up and go all the way to the left, where did my Zoom meeting go? There we go. So if we pull this Excel file up, and instead of being over here, if we go all the way to the left where it says CORREL chart, correlation chart, here I have some updated, some more recent data that I just pulled this morning, actually. So this is Spider Gold Shares, Google, Tesla. Tesla's pretty cool these days. Amazon, and again, PIMCO's high yield bond fund. And we also have the silver, iShares Silver here, which does kind of the same thing as the Spider Gold Shares. This company iShares buys silver, holds it in a vault somewhere, at least they say they do. And you can buy what's essentially like a stock that is a proportion of that holding. And we can see here I've gone over 2 years. So the last 2 years worth of weekly data. And we can see, for instance, if we look over here, we can see, oh, I bolded the ones that I was interested in. Let's unbold those. We can see this correlation chart. That's often a nice way to look at correlations. I can see the correlation between, say, silver and gold is 0.9. That's quite close to 1. That's what I would expect, actually, right? Yeah, I mean, they're both bullion. They're both kind of safe haven investments, precious metals. So I would expect that when, if I'm looking at the market and silver is high, gold is probably also going to be high and vice versa. If silver is low, gold will probably also be low. Was quite high right before the election when people's fears and uncertainties were the highest. So that was a good time to sell your gold or silver if you were holding. We see that, for instance, silver and Tesla only have a correlation of about 0.2, much lower correlation. Because, I mean, Tesla's value is quite independent of silver, right? Silver is kind of a safe haven investment. It's a question about what's going on in the market and how much fear and uncertainty there is among the population of investors. Tesla's they're kind of their own thing. I don't even understand how Tesla stock works. Obviously they're in the electric vehicle business, but it kind of seems like, almost no matter what they do, their stock just keeps going up. But so you see Tesla not really related to silver, with a low linear relationship to silver or gold. You also see them with a fairly low relationship to Google, Tesla and Google right here, and with Amazon, and also with PIMCO, a relatively low linear relationship between all of these. But then we see again, like say Amazon versus PIMCO, pretty high linear relationship there, high degree of linear relationship. These relationships are all positive, actually. We could have maybe thrown a couple other metrics in here, maybe like the VIX, the volatility index. That might have been negatively correlated. That might have been like when the volatility index, which is kind of an indicator of people's kind of fears about the market. Maybe when that's high, the market tends to be low and vice versa. Kind of interestingly, from a finance perspective, bonds tend to run opposite stocks. So it tends to be the case that when the stock market is fairly high, bonds have a lower value because people don't really want to invest in safe bonds with a defined rate of interest. They want to ride the stock market when the stock market's doing well. And when the stock market's doing poorly, people flock to bonds for kind of the more safe haven, the defined rate of interest that they yield. So you'd almost expect a bond fund to move opposite the stock market. You'd expect a negative correlation here, but we see a positive correlation. And I chose this one in particular because this is a high yield bond fund. So these are companies that are paying high interest rates, and they pay high interest rates because they're in a bit of financial distress. Maybe distress is a little too heavy-handed, but they're not in the most solid of financial states to be asking to borrow money from the market. So, uh, if the economy goes south, these are going to be the first companies that are not able to satisfy their debts. So these bonds actually run more like stocks. When the market's doing well, these companies can probably kind of continue to float along and satisfy their debts. But if the market crashes, these are going to be some of the first ones to flop. So a high yield bond fund or a low grade bond fund, high yield is just a, euphemism for low grade debt. Um, so a high yield bond fund is going to look more like a stock holding than say a typical bond fund. If you're investing in debt from GE or Amazon or somebody like that, that's going to be much higher grade debt. It's going to pay lower yields, but it's much safer, and that's going to run opposite the market. Who wants to, you know, lend money to GE at 3% when you could be getting 10 or 12% in the stock market? That's not a very attractive offer when the market's doing well. Okay, so let's take a look at number 2 here, correlation worksheet. Let's get that to load. There we go. So pull this up and take maybe a minute or two and take a look across this worksheet and try to line up which of these 5 correlations goes with which of these 5 scatter plots. So take about a minute or so, take a look at it and try to line these up. Okay, let's take a look at these. So I have 5 correlations here. I have a 0. I have 2 positives, 0.96 and 0.8, and I have 2 negatives, negative 0.98 and negative 0.74. As kind of as an aside, it would not at all be a fair question for me to just like show you this scatter plot and say like, what's the correlation? Or even what's the correlation plus or minus 0.05 or something like that, right? But if you have 5 scatter plots with 5 fairly different correlations like this, you should be able to match them up. So this is a different question than saying, here's a plot, what's the correlation just by looking at it? That's not a reasonable question to try to answer. One thing that we can sometimes do that can be a help if we're having trouble teasing this out, teasing out which one goes with which. One thing I can sometimes do is I can pick something that looks roughly like the middle or almost like the center of mass of these points. Maybe somewhere like here, that looks like it's kind of in the middle of all the points. I can draw a vertical line and a horizontal line. And I could ask myself in which quadrants I see more data. I see a lot of data in quadrants 1 and 3, and not very much in quadrant 2, and almost nothing in quadrant 4. I mean, those ones that are in quadrant 4 are only in by a tiny bit. Right? A straight line that goes through the origin that goes from quadrant 3 to quadrant 1 would have a positive slope. So I think there's probably a decent degree of linear relationship and probably a positive linear relationship here. If I were to look at, say, this one, if I do the same thing, pick about the middle, draw a horizontal and vertical line, I see essentially everything is in quadrants 2 and 4. That's associated with a line with negative slope, negative linear relationship. And if I were to do the same thing with, say, this bottom middle, again, if I pick the middle of the data, maybe it's something like here. I actually see that I have like about the same amount of data, maybe in all 4 of my quadrants are pretty close. Maybe the middle of my data was just a tad higher than that. But I don't see really any evidence of the linear relationship. Like a line with a negative slope is going to go through quadrants 2 and 4, but miss all of the data in quadrants 1 and 3. And a line with positive slope will hit quadrants 1 and 3, but miss 2 and 4. I'm missing like half of my data no matter what I do. I think there's no evidence of a linear relationship here. So bottom middle would be no evidence of linear relationship, magnitude near 0. That's going to be my 0 correlation on the bottom middle. I see that top middle and bottom right both have what looks like a positive relationship, more data on the top right and bottom left, and less or none in the top left and bottom right. Those are going to be my positive correlations. Whoops. Those are going to be my 0.96 and 0.8. Which one goes with which? Well, we're not looking at the slope of the line. It's not like the steeper slope gets the higher number. It's the one that looks more like a line. The bottom right looks a lot more like a line. If I drew a straight line through here, the data points would be much closer to that line than any straight line that I could draw in the top center. So bottom right is going to have the higher positive correlation, 0.96. It has a higher degree of linear relationship between the two variables, and it's a positive nature. And my top middle still has a decent degree of linear relationship, not quite as linear as the bottom right, but still a decent degree and still positive. That's my 0.8. And then likewise, my 2 on the left here are my negative linear relationships. Very strong degree of relationship on the top left, and a little weaker degree of relationship on the bottom left. And they're both negative relationships. So these are going to be D and E here, negative 0.98 and negative 0.74. The negative 0.98 that in magnitude is closer to 1, that's going to be associated with the top left, which if I drew a line going from top left to bottom right, these points are going to be all very close to that line, where bottom left, if I drew a line through this data going from top left to bottom right, there's going to be more scattering of the data a little further away from that line. So still a decent magnitude of relationship, but not quite as high of a magnitude as the top left. So that bottom left is going to be that negative 0.74 correlation. Okay, so we discussed correlation coefficient. Today, when we come back, we're going to make the jump to discussing the regression line. We're going to use the idea of correlation and also this rough amorphous idea of drawing lines. We're going to try to draw a regression line. We're going to try to make a linear model that models this relationship between X and Y. And I was hoping we get to this today, but we didn't quite. The kind of quotes of the day for today are "The World is Locally Linear" by Professor Layton, or this other funny one, which we'll get to next time. Okay, so just remember, finishing up correlation regression next time, a couple more small topics. The videos for those topics are posted on the YouTube playlist if you want to watch those ahead of time. And the final exam is coming up, so make plans for that. I will see you all on Wednesday. Have a good one.